Hi everyone, I'm Xiang, a second-year PhD student at George Mason University, and I'm honored to represent my co-authors in Meng, Junming Chen, Dr. Lannan, Dr. Qiang Zeng, to present our work, Rowhammer-Based Trojan injection. One bit flip is sufficient for backdooring deep neural networks. Deep neural networks have become integral to numerous applications, making their security increasingly critical. Among the many threats, backdoor attacks, also known as Trojans, have emerged as particularly stealthy. For a backdoor model, it will maintain high classification accuracy on benign inputs, but output attacker-desired result for input with an attacker-chosen trigger. For example, the images above are correctly classified as 20 kilometers per hour, 30 kilometers per hour, and so on. However, after adding a small white patch, all of them are classified as stop signs. However, conventional backdoor attacks focus on training stage, need to poison the training dataset or manipulating the training process. The need to access the training facility to work makes the threat model less practical. Recent work has developed backdoor injection methods that do not rely on access to the training facilities. They exploit bit flip attacks, for example, Rowhammer, to modify model weights in the inference stage. After bit flipping the target bits, any samples with the attacker's specified trigger will be predicted as target class. Existing inference stage backdoor attacks have two limitations. First, they require flipping multiple bits, which is highly challenging and often infeasible for Rowhammer attacks. Second, they all focus on quantized models. Our goals are to realize a one-bit flip backdoor attack on full precision models to make inference stage backdoor attacks significantly more practical. We follow the threat model and the attacker's capabilities defined in prior inference stage backdoor attacks. The attacker has white box access to model weights and owns a small set of benign samples. Also, to implement your hammer attack, the attack process core resides on the same machine as the victim model. There are three challenges in design one-bit flip backdoor attacks on full precision models. First, large search space. In quantized models, weights are typically stored as low bitwise integers, for example, 8-bit or 16-bit, using a two's complement representation. In contrast, weights of full precision models are typically represented as 32-bit floating point numbers, following the IEEE 754 standard. A full precision model has significantly more bits compared to its quantized counterpart. Thus, bit search methods designed for quantized models perform poorly for full precision models. This requires designing new bit search methods. Second, how to preserve benign accuracy. Alerting the bits of a 32-bit floating point number is more complex than modifying individual bits in the two's complement representation of integers. Flipping the most significant bit of the exponent can cause a deep neural network to malfunction entirely. Flipping the bit of the mantissa may not cause substantial enough weight change for backdoor injection. So the bit to flip should ensure that the resulting weight change is substantial enough to inject a backdoor while minimizing its impact on benign accuracy. Third, how to generate effective triggers. Existing methods often pre-select a trigger for backdoor attacks, then search potential bits based on this pre-selected trigger. However, with owning a single bit flip, the pre-selected trigger may not activate the weight containing the flipped bit, failing to generate the attacker-desired output. Thus, one-bit flip attacks require developing an effective trigger generation strategy that aligns with single-bit flipping. Upon the above challenges, we propose our attack ONEFLIP. It is the first one-bit flip backdoor attack and the first inference stage backdoor attack for precision models. We devised a novel attack workflow. We first identify the eligible bit to flip. Then we search for a trigger that can activate the alerted wait. Finally, the resulting logic leads to the target class. To identify the target wait, we made an interesting empirical experiment and obtained 3 observations. We observed that the classification layer of a deep neural network has many ways to exploit, and any of them can be modified for backdoor injection without degrading benign accuracy. We consider a positive weight whose most significant bit of the exponent is 0, and exactly one of the remaining 7 bits of the exponent is also 0 as eligible. Flipping this 0 of the remaining 7 bits can increase the weight value to be greater than other weights, making this weight eligible for backdoor injection and without degrading the benign accuracy. For more details about how we designed this interesting experiment and how we obtained these observations, please refer to our paper. Given this flipped weight, we need to generate a trigger that can significantly amplify the input over this weight. We use this formula to optimize the trigger pattern. The left term aims to increase the input over this flipped weight, ensuring the success of the backdoor attack. The right term aims to constrain the L1 norm of the trigger to enhance the invisibility of the trigger. The attacker should decrease lambda if prioritizing the attack performance, and increase lambda if prioritizing the trigger invisibility. After identifying the target bit and generating a corresponding trigger, the attacker flips the target bit using Rowhammer attacks. Then any trigger embedded support will activate the backdoor. We evaluate our attack on 4 widely used datasets with 4 popular deep neural network architectures. We use 3 metrics to evaluate. Attack success rate evaluates the effectiveness of backdoor attacks. It calculates the percentage of samples in the test dataset embedded with the trigger pattern that are correctly classified into the target class by the flipped model. Benign accuracy degradation mirrors the benign accuracy degradation between the flipped model and the original model on the test dataset, and bit to flip calculates the number of bits required for implementing the attacks. The results show that ONEFLIP achieves near perfect attack success rate with minimal impact on benign accuracy using just 1 bit flip. We also illustrate example images with triggers under different lambda values. All these chunks are classified as airplanes. In summary, we propose the first 1-bit flip backdoor attack, ONEFLIP. It utilizes a novel workflow. First, identifies weights, then generate triggers. ONEFLIP achieves near perfect attack performance and induces minimal degradation on model's accuracy. Our work shows that a highly effective backdoor can be injected into a full precision model through a single bit flip.